Yes, hello. My name is Tim Graulich. I'm from DTU in Denmark, and I'm a PhD student under the supervision of Marie. I'm part of the Muesli project organized by Cresm here, and we investigate machine learning-based surrogate models for large-scale sector-coupled energy systems. So a lot of this has already been said by Marie. We expect sector coupling to imply a lot of changes to our energy system, and this means also a lot of challenges and opportunities for our actors. And so there are a lot of investments needed, and we want to support these actors through models in their decision making. Right now, we already have a lot of models that are modeling different sectors, but also different sector coupled systems. And these models are, especially on larger scales, very complex. So to make them more usable, we want to simplify these models. And finally, we already have a lot of validated and good models for the different sectors and a lot of knowledge and tools distributed among actors. So we don't want to invent completely new models, but we want to reuse these models. And this is where the model linking comes in. Shortly about the Muesli project, it's just recently started. It's a collaboration between DTU, TU Delft, Comias, and Total Energies, RTE, and GRT Gas. And the question it wants to answer is how to design and plan the energy infrastructure towards a carbon neutral society while accounting for sector coupling. And from a modeling perspective, what we want to keep in mind is that our models should be computational tractable, so they're usable. They should have high accuracy or resolution. And they, of course, should be open source and as general as possible so they can be used for different applications. Now, where my research comes in, we want to build machine learning-based surrogate models, which can be thought of as an estimation of an already existing energy model while reducing the computation time needed to get the results. Our proposed workflow can be divided in 3 different steps. First, we want to generate data from an existing energy model using some kind of global sensitivity analysis and Monte Carlo simulation to get a large data set of input and outputs of different scenarios. And then in the second step, we want to build our surrogate model using machine learning. Could be an artificial neural network, but there are different methods that we could use. And we can then validate it against our original model in terms of output results, so accuracy, but also computation time. And once we have the surrogate model set up, what we want to do is we want to link it to another energy model of a different sector. So we want to supply this energy model with additional information from our surrogate model. But since we expect our surrogate model to be very fast in computation time, we want to do that without increasing the computational time of the overall coupled model too much. So this is the idea. Some ideas that we have in terms of modeling of the surrogate model. We want to look into Bayesian learning, which is a sort of stochastic estimation, where we could actually get an uncertainty estimate of our output that would allow us to perform something called hybrid linking. So instead of just linking the surrogate model to the existing energy system model, we can, in case our surrogate model is very uncertain about its output, we can actually swap in our original energy model to make sure that we get good results. We want to look into something called constraint learning, where in the training process we already supply our surrogate model with the constraint contained in our original optimization model that would speed up the training process and also allow for more robust results that would ensure that they actually fulfill our constraints. And finally, we want to look into graph neural networks. Since most of our energy systems are structured in networks, we want to capture this characteristic of the energy system by using these models. So yes, thank you.